Hi everyone. Today we will continue our discussion on chem informatics. In the previous lesson, we looked at a synthesis planning approach that uses an enhanced graph neural network called chemical reaction aware molecule representation learning. We trained the model using the USPTO 50K dataset. For this lesson, I had planned to focus on the prediction code, but I will also walk you through a few subtle updates made to the training code with the help of Jules from Google. This material is based on the journal article written by Wang et al., published in an open access preprint repository AR14 in September 2021. Let's do a quick review of the reconstructed MolR training code. First, we load reactant product pairs. These are converted into graph objects using smiles_to_graph function. As shown in the previous lesson, multiple reactants connected by a dot can be merged into a single graph. After training with that approach, I ran predictions, but the generated products were much larger than the intended targets. To address this, I tried another method. Instead of merging, I separated reactants connected by dots and generated multiple graph objects. Each reactant graph is then processed individually by the graph neural network to create embeddings. These embeddings are summed before calculating the contrastive loss. This compares correct reactant product pairs against incorrect product reactant pairs. The model then optimizes and updates the weights and bias across the neural network layers, and these optimized and updated weights and bias are saved, and then with that we start another approach. This process repeats for a number of approaches specified. When training is completed, the graph neural network's final weights and biases are saved for later use. Let's walk through the updated MolR training code. We begin by importing the custom modules and required Python libraries. Next, we read and parse the USPTO 50K dataset. The reactions are converted into molecular graph using USPTO graph dataset function, along with the smiles_to_graph function. USPTO graph dataset function is here, which is actually in the module data loader. The key difference from the initial code here is that the reactants connected by dots are split into separate entries. And then these individual reactants are included into the list and stored as a set. Reactants_graphs, product_graph. We then prepare the data for batching and shuffling. Each batch contains 32 reactant product pairs. Collate_pairs function organizes each batch into two lists, one for reactants, one for products. After that, we instantiate the graph neural network model and configure the optimizer for training. The training loop proceeds approach by approach over the batches. Each batch is passed through the graph neural network, which embeds reactants and products into vector representation. Here we embed product batch, and then here we embed reactant batch. When there are multiple reactants, their embeddings are summed before comparison. We compute the loss using the contrastive loss function with a margin of 0.5. This function assigns positive scores to correct reactant-product pairs and negative scores to mismatched pairs. To challenge the model, the loss uses the hardest negative within the batch, the product most similar to a given reactant, and the most likely to cause confusion. Gradients are then backpropagated, and the optimizer updates the model's weights and biases. Finally, at the end of each batch and each epoch, the trained results are saved to the MTL folder. Let's take a quick look at the MolR prediction code. This is similar to the training code, but is slightly simpler. First, we load and parse the USPTO 50K dataset. But this time, we only extract the product molecules. Next, we load the trained model, especially the weights and biases from the graph neural network layers that were saved for training. Then we convert the product molecules from the USPTO 50K dataset into graph objects and embed them using graph neural network. After that, we select a reactant product pair for prediction from the testing dataset. We only isolate the reactants and convert them into graph objects, and then embed those using the same graph neural network. For the prediction step, we compute the Euclidean distance between the embeddings. I actually experimented with contrastive loss function, cosine similarity function, and Euclidean distance. And among this, I found that the Euclidean distance performed the best. It consistently produced products that were at least similar in size to the target molecule. And then the code generates 5 closest candidates. Let's walk through the updated MolR code. First, we read and parse the US50K dataset. Then we only isolate products from the dataset after splitting reactants from products. Then we load the weights and biases of the graph neural network layers from the training. Here we load the results from 1281st epoch. Then we convert the product into the graph objects, and then we embed the product graph objects with the graph neural network model. Then we select the reactants product pair for the prediction. We isolate the reactants from the pair to generate graph object. Then we embed the graph object with the graph neural network model. We then calculate the Euclidean distance between the reactants embedding and the product embedding for prediction. Then we generate top 5 candidates for the product and write them in the output file. Okay, let's run the code by clicking the play button. I'm going to actually use 2 different prediction code. The first one uses cosine similarity, and the second one uses Euclidean distance. First, we test the model using the cosine similarity. The run is complete. Let's see the results. From these two reactants, we expect these results, but we obtain a bit larger molecules. C10, C17, C18, C13, C35 instead of C8 compounds. Okay, let's test the code using Euclidean distance. The run is now completed. Let's take a look at the results. From these two reactants, we're expecting this C8 compound. This gives us a product that is at least close in size to the target compound. However, unlike models such as molecular transformer or agents finder, this approach did not produce the exact target product. They're all different from the target compound. It is possible that the original implementation by Wang et al. Performed better, but even in their paper, they noted that the model often returns similar compounds rather than perfect matches. In summary, as shown, the proposed MolR chemical reaction-aware molecule representation uses graph neural network as molecule encoder. By training the graph neural network encoder to minimize the residual of the sum of the reactant embedding and the sum of product embedding, which is close to zero for a specific reaction, the model implicitly learns exactly what changes or what does not change at and around the reaction center, which is referred to as implicit learning. The model applies positive and negative sampling to guide optimization. This helps organize the embedding space by grouping chemically equivalent molecules together while separating non-equivalent combinations. Since regions of the molecule far from the reaction center do not affect the transformation, knowledge from one reaction can generalize to a broader class of similar reactions. For example, what MolR learns from the reaction between propanol and propanoic acid can extend to other alcohol and carboxylic acids. In this way, MolR implicitly learns reaction templates, which are key for generalizing to unseen reactions. However, the reconstructed code shows limited generalization. The model trained on the USPTO 50K training dataset could only predict compounds with a similar molecular size rather than exact target structure, which we have seen from agents finder code and also molecular transformer code. Thank you for your attention. I hope you found the session engaging and informative.